So have you ever been there? You've got this massive data set, a really powerful model, you hit train, and then you just watch that progress bar crawl. I mean, for hours, sometimes even days. It's a huge bottleneck in machine learning, right? But what if I told you the standard way of doing things is often the problem, and there are much, much smarter ways to get your model to learn? So why does that happen? Why does adding more data, even when you have great hardware, bring model training to this grinding halt? Well, the answer really comes down to how the most basic learning algorithm processes all that information. Okay, let's dive into this.
First up, we've got the classic, the most straightforward approach, batch gradient descent. You can think of this as the measure twice, cut once method, but, well, taken to a pretty wild extreme.
What does it actually mean to process the entire data set for just one single update? Okay, imagine you're trying to find the fastest way down a mountain. This method is like stopping, pulling out a massive, super detailed map of the entire mountain, calculating the one perfect direction to step, and only then taking one big, deliberate step.
Now, here's the really interesting trade-off. That single step you take, it's very, very accurate. It points you directly toward the bottom of the mountain, giving you a really smooth, stable path. But the cost? It's incredibly slow, and it eats up a ton of memory. For the millions of data points we use today, stopping to read the entire map for every single step, well, it's just not practical.
So if that's just too slow and deliberate, it kind of begs the question, right? What happens if we do the exact opposite? Is there a faster, more, reactive way to get down this mountain?
And that brings us to stochastic gradient descent, or SGD for short. This approach basically throws that giant map away and just goes for pure speed and reaction. So how does this change the learning process? Well, instead of looking at the whole map, this is like only looking at the single pebble right underneath your foot to decide where to take your next tiny step. You're updating your direction after every single piece of information, no matter how small it is. The result of this is you move incredibly fast, taking maybe thousands of tiny little steps in the time batch gradient descent takes to make just one. But the path is erratic. It's really noisy. Instead of a straight line down the mountain, you're zigzagging all over the place. That cost function, the thing that measures our error, it just oscillates wildly as the model reacts to every single data point.
And here's the paradox, the kind of crazy part. While the individual updates are happening all the time, the path is so unstable and inefficient that the total time to converge, to actually get to the bottom of the mountain, is often much, much longer. It's a classic case of more haste, less speed.
All right, so we've got two extremes on the table. One is super precise but painfully slow. The other is fast in theory, but it's just too chaotic to be efficient. Surely there has to be a balance, right? A sweet spot somewhere in between?
And of course there is. It's called mini-batch gradient descent. And this is the approach that powers the vast majority of modern deep learning. It finds this brilliant compromise between those two extremes.
So how does this fit into our mountain analogy? This is the pragmatic choice. You don't look at the whole mountain, and you don't look at just one pebble. Instead, you look at a small patch of ground right around you, a mini-batch, and you use that information to decide the best immediate step to take. And this, right here, is why it's the default choice for almost everything. It gives you a much more stable path than that wild zigzag of SGD, but it's way more computationally efficient and faster than the old batch method. It really is the best of both worlds.
Okay, so we've talked theory, we've used our mountain analogy. Now, let's look at some cold, hard numbers and see how these three methods actually stack up in a real-world test.
Check this out. This table shows the results from training a model on an image dataset for 100 passes. Look at mini-batch. It hits a solid 85% accuracy in just under 3 minutes. Batch GD gets a little more accurate, but it takes longer. And then there's SGD. It's the slowest by a huge margin, taking 35 minutes just to get to 80% accuracy.
This chart really makes that difference in runtime crystal clear. I mean, the time required for SGD is just in a different league. It's an order of magnitude slower for the same number of passes over the data. Mini-batch is the obvious winner when it comes to efficiency.
So let's bring it all together. This is the ultimate takeaway right here. Batch gradient descent gives us that stable but slow path, which really only makes it useful for small datasets. Stochastic gradient descent is noisy and, as we saw, surprisingly inefficient. That leaves mini-batch as the clear champion, hitting that perfect sweet spot with the best balance of speed and stability for modern machine learning.
At the end of the day, by breaking the problem down into these small, manageable chunks,
Mini-batch finds the most efficient path to the solution. For any kind of large-scale learning, it's simply the smarter way to train your models.
But here's the thought. Finding the best path, choosing between batch, SGD, or mini-batch, is really only half the battle. This just tells us how much data to look at for each step. It doesn't tell us how to actually take the step itself. And that brings up a whole new question.
That next question, which is all about optimizers like atom and momentum, well, that's a topic for another time. If this explainer helped you get your head around the different flavors of gradient descent, be sure to like, share, and subscribe for more. Thanks for tuning in.